Good evening on a rainy evening. It's great to see this turnout for the President's Faculty Lecture Series here at Surrey. And let me start by acknowledging that we are indeed privileged to be gathered on the traditional unceded territories of the Coast Salish peoples. I also want to say a special welcome. I understand we have students here from the grade 11 and 12 students from the robotics team from North Surrey Secondary. You out there? Great. All right. So an informed audience already with us. That's great. It's my pleasure to welcome you to this event with Professor Richard Vaughan, who's going to address us shortly on a really intriguing subject, robust interaction in human and robot teams. I'm looking forward to finding out what that's all about myself. This event, as you may know, is part of SFU's commitment to be Canada's most community-engaged research university. The President's Faculty Lecture gives us a chance to share with the community some of our faculty members who are doing really exciting research and work. And it also gives us a chance to show to the community that we are trying in every way we can to engage and to add benefit to the community. It's part of a larger initiative, SFU Public Square. SFU Public Square does programming throughout the year all over the Lower Mainland. So if you check out their website, you can find out about a whole bunch of other opportunities that occur. I'm Andrew Petter, president of SFU, and it's always a thrill for me to be able to attend the lecture series and to find out what our faculty members are doing. And there will certainly be a chance for you to ask questions at the end of Richard's presentation. We will also have an opportunity, hopefully afterwards, to have a few light refreshments. And I would also just note that this lecture is being filmed. So if you do ask a question, you may end up on camera, which is, depending on how you feel about that, either an added plus or something that's going to give you a bit of pause to think about your profile. So let me tell you a little bit about our guest lecturer for this evening. Dr. Richard Vaughan is a professor in SFU's really world-regarded School of Computing Science. He also recently joined Apple in a leadership role. His research interests include multi-robot systems, human-robot interaction, robot software engineering, and behavioral ecology. Richard demonstrated the first robot control of animal behavior using a robot sheepdog. Oh, they have long hair? I don't want to know. He also co-developed the Player Project, a widely popular software for research into robotics and sensor systems. He was Program Chair of IROS 2017 Vancouver, the largest technical robot conference to date. And he's previously held positions at HRL Laboratories in California, at the University of Southern California, the University of Oxford, and the University of Sussex. He's founder and director of the Sfu Autonomy Lab, whose goal is to increase the capacities and robustness of mobile robot systems. The lab is part of the NSERC Canadian Field Robotics Network, which is a group of academic, government, and industrial researchers who are working to develop robots to perform tasks and gather data on land, in the air, and on or under water. God, what Richard doesn't know about robots, I don't think exists. While working to build smarter and more resilient robots, his Autonomy Lab also trains and supports students in this cutting-edge field. So for all these reasons, and so we can all learn more about his work, I'm just thrilled to be able to introduce him to talk about robust interaction in human and robot teams. Please join with me in giving a warm Surrey welcome to Dr. Richard Vaughan. Richard?
Thanks very much, President Petter, for that warm introduction. It's great to be here. Thank you all for coming out on a rainy night. It's good to see you. Can you hear me okay at the back? Okay, thanks. It's great to see the high school students here and the even younger kids at the back. So thank you for coming out to see us. So it's common, those of you who go to academic talks a lot will know that it's common at the end for a professor to say, of course, all of this work was done by my students, and put up pictures of them. That usually happens at the end. I want to put them at the beginning so you can picture these faces while you look at the work. So there's a bunch of these guys are here. Why don't you turn around and wave, everybody. So this is a bunch of guys from my current lab right now, here. And this is the last few last few years' worth. So I'm the front person for a team of excellent students, and here they are. I'll mention their names as we go along. So what I want to talk to you about is, I'll lead you through a story of a subset of my group's work, where we've been interested in studying how humans can interact with robots and teams of robots in a way which requires very little effort on the part of the human. So kind of natural, easy interactions. And the inspiration we're going to use is from culture and history of how humans have interacted with other intelligent systems. And I'll explain what that means in a minute. So first consider a robot from culture that is beyond the state of the art. This is the Baymax Robot from what wonderful film, Big Hero 6. If you haven't seen it, do yourself a favor. Loads of great robots in there. There's some nodding from the high school kids here. So Baymax is a terrific robot beyond the state of the art. Baymax is a squishy inflatable robot, which is a source of lots of gags in the movie. It's actually based on a real robot from CMU that really does look kind of like that. It's an inflatable, white, squishy robot. But the behavior that Baymax produces and the way Baymax interacts with his human friend is way beyond the state of the art. So it's not something that we can push towards right now, but we'd like to get there in the future. I'll come back to it at the end. When I was a kid, this is what state of the art in human-robot interaction in the artistic endeavors was. So this is one of the crucial scenes in the Star Wars universe when Princess Leia entrusts the plans to the Death Star, the new secret weapon, and gives them to R2-D2. And this interaction is very, very high stakes. This has to work. R2-D2 has to understand what she wants. She's going to give her the secret plans. She stuffs it in a USB port or whatever it is in R2-D2. And R2-D2 has to understand, and Leia has to be confident that he understands, because this is very, very serious, right? And for the rest of the Star Wars series, things, as a consequence of this interaction, a bunch of very important things happen. So now, R2-D2 doesn't talk, right? But you understand what R2-D2 is thinking and feeling, kind of, right? R2-D2 understands what people are thinking and feeling, for sure. So R2-D2 he can't do everything that people can do, but he can do a subset of it. And importantly, R2-D2 is a robot you can interact with in a robust and straightforward way. Now, so that was, Star Wars is from 1977, I think. This is from Fantasia, a Disney movie from 1940, where there's a wonderful sequence where Mickey Mouse commands a bunch of intelligent brooms. So these are the kind of 1940s magical Roombas of their day, right? They're autonomous systems powered by magic rather than engineering that can sweep up the castle where Mickey is working. And Mickey interacts with his brooms in a gesture-based interface. He commands them like this. And the audience can understand what the intent is, and these magical brooms can understand what the intent is. They don't understand speech, but they understand gestures. We can understand what gestures are. So that's sort of, a couple of samples from 20th century culture. But humans have been interacting with intelligent systems in very complex ways for a long time, for many thousands of years. If you've ever seen, I hope you have seen a professional sheepdog, shepherd and sheepdog system working. It's absolutely amazing how competent they are. The sheepdog has a simple vocabulary of commands, maybe 20, 25 different commands. Things like go around to the right, go around to the left, go closer, come further. Simple commands like that. And the system is incredibly effective. The sheepdog does a lot of work by itself, and the shepherd does some high-level stuff, like guiding the whole thing. It's a wonderful system used in many cultures over thousands of years. Similarly, this works with air systems. So this is an autonomous agent that flies in the air, which is popular these days, drones. Most cultures have hunting with hawks. And the thing that's remarkable about these is the range over which it works. So this human can call down this hawk from maybe 400 or 500 meters away, maybe even further. At that point, the human can barely see the hawk. It's just a dot. However, the hawk has got much, much better eyesight than you. So the hawk can see you very clearly. You do gestures like this, and the hawk will come down, because every time you've done that previously, you've had something tasty in the palm of your hand. Right? You train the hawk like that. And the hawk understands some audio commands as well. So humans have been working with intelligent systems animals, trained animals, for thousands of years. There's another really interesting motivating example. Companion animals and trained animals to assist people with various disabilities play an extremely important role in the lives of people that use them. And we have very, very well-developed systems for training these animals and for interfacing with them. And the guide dog for the blind is just one example. There are many, but there are lots of examples to go out looking for them. So we'll take inspiration from these things when we design robot systems. We want robot systems that are easy to use in the same way that these things are easy to use. It's not a lot of work to operate a guide dog if you know how to do it. Okay. So human-robot interaction is quite a popular field. In fact, I think after deep learning, the big conferences these days, the second most popular subject after deep learning is human-robot interaction at the conferences. Most of the work in the human-robot interaction is exactly like this. It's a robot and a human, and they're attending to each other, often across a table, sometimes with colored blocks, sometimes maybe there's something that you want to screw together. So most human-robot interaction is exactly like this. So maybe 95% of it. I'm interested in the remaining bit. So I'm interested in gaining and manipulating the attention of robots, and for robots to do that to people. So what's the point of that? Well, Leia didn't wake up this morning face-to-face with R2-D2. They had to get into this situation. So if 90% of HRI, human-robot interaction work, is on this, this intimate one-on-one, fully attentive interaction, let's do some of the missing part, which is how do you get there in the first place? How do you get the attention of a robot, manipulate it, and vice versa to get into this situation? So that's what we were working on. So here's an example. This is from Elizabeth Croft's lab at UBC. Elizabeth works on being able to work in close proximity with a robot, maybe assembling something together or working in manufacturing. And the problem Elizabeth studies is how can a human work closely with a robot without getting their arms broken all the time, right? Because if the robot bonks you, that's serious business. So this is a PR2, its arms are a little bit springy. You still don't want it thumping you. So Elizabeth works in this thing. So I'm doing the other stuff that Elizabeth isn't doing. She does it very competently. So here's an example of the first piece of work we did in this area way back in 2010. And this is Yaroslav. He's giving waving commands. So he waves either to the right or to the left, and the robots will go and do a job on the right or the left. But only one robot at a time is going to take the command from him. Can you tell by looking how is he getting the attention of a robot? How do the robots decide who should take the command right now? Yeah, it's almost a trick question. He just looks at the one he's interested in, right? So it's so obvious. It's so obvious, of course. So I can look at somebody from the crowd. I'll pick you, sir, unfairly. Now, everyone else in the room knows that I'm not looking at them. And you know very well, too well, that I'm looking at you right now, right? It's so simple and super powerful. Our brains are very, very, very sensitive to that. So how we do this is each robot estimates how directly the person is looking at it. And we have very, very good face detectors. If you haven't thought about this before, you may not realize this, but faces are designed to be looked at. So there's a chunk of your brain which is devoted to looking at faces, and your face, the shape of it, has evolved in parallel with that piece of brain so that they're exquisitely tuned to each other, right? So your face, you have this vertical stripe, you have a dark shadow down one side of your nose, your face pops out. My brain is very good at seeing all of your faces right now. So faces are designed to be looked at. So it's one of the easiest things to do is to see faces in computer vision. Excuse me. So we can see here the shock effect is looking directly at this camera, less directly at that camera, and not very directly at all at this camera. Now the robots have a superpower that animals don't have. They can talk to each other across the wireless network very, very quickly. So what these robots do is trade these numbers in a way which is guaranteed to be, under certain constraints, is guaranteed to be reliable and optimal. And they will choose the one with the biggest number. And that's the person who has the human's attention right now. The cool thing is that this happens in less than 300 milliseconds, so the person doesn't really perceive it. So if you have the robots in front of you, as you look from robot to robot, the robot you're looking at, the lights come on, and you don't feel it as a person. It's just as if the robots all have their lights on. It just works the way you would like it to. So that was a system where we picked one robot from a group. And it was the first system where you could get the attention of a robot without any instrumentation. We didn't have a laser pointer, or we didn't wear a traffic cone on our head, or yellow gloves or anything, all the things that make robotics easier. Our discipline is you just you have to be just wearing the clothes you were wearing today. So this is the first example of being able to choose a subset of the robots. Now we're choosing a group instead of exactly one robot. So Brian is choosing first the right-hand pair, like this, and sends them to the left job. And then the left-hand pair and sends them to the other job. Now this is also a simple trick. It's a trick once you know it, but it works really well. So we're able to see faces, as I mentioned. We're also able to track the hands. Under reasonable lighting assumptions in the lab back in 2011, we were able to track hands fairly well. So the trick we did was to, let me try this. If I select you guys, now you guys know that it's not you, right? You guys know that it's you. Maybe there's some people on the edge and maybe you're in, maybe you're out, not quite sure. Can you imagine how I'm doing that? How do you know? So there's a simple trick. If my face is inside the ellipse prescribed by my hand, you're in. If it's outside this ellipse, you're out. Super simple, right? But it works really, really robustly. So this is the first example of choosing a group of robots from a population, and it works pretty well. Now, the downside of this is that if you're on the edge, if my face was neither inside or outside, it's kind of on the edge somehow, maybe I chose a couple of people by mistake. There's no way of modifying these groups now. So the next thing we set out to do is to choose groups and then be able to modify them if you got it wrong. So Shokafir says you two to the robots. And which two does she mean? Well, it's the two that she's looking at. Take off. So which two take off? The two that she was looking at. So how we do that is we do 2 rounds, or n rounds, where n is the number she says. We do n rounds of the election until we have enough people there in the group. And now she's going to do it again. This time she says you 3. Now, please forgive this. It's a little clumsy. The robot's cameras actually point down, so they don't see her very well. So it takes a few seconds for all the robots to see her. She said you 3. Now she's going to go to the middle robot and say, not you. So she's now modified the group. It was 3, now it's down to 2 because she said not you. Okay, and what does you mean? Well, you is the robot that you're looking at right now, of course, using the method we said before. Okay. So that was all with ground robots, and with the camera. The cameras are all stationary in the examples that you saw. It's a much bigger challenge to work with moving cameras because on a camera that's moving, the color of every pixel changes in every single frame. Right? You never see the same thing twice on a flying robot. So here we're going to, so this is the first example of an uninstrumented user, like a barehanded user controlling a robot in flight. These 2 robots take off and they stabilize themselves in the room and they're looking for human faces. When they see one, they try and keep the human face in the middle of their field of view. These videos here is exactly what the robots are seeing right now. And then Manny is going to use his right-hand wave means add yourself to the team. And the robot he's looking at will add itself to the team. So now the team has 2 robots in it. And he's going to use a left-hand wave to remove that robot from the team. And he adds it back to the team. And then this wave means execute a mission. And the mission is spectacular but short. The batteries don't last very long in this case. So that's the first example of an uninstrumented user controlling the behavior of a flying robot ever. So we've a progression over 3 years of picking one robot from a team, picking multiple robots from a team that are next to each other, and picking arbitrary robots from a team and then modifying, adding or removing the teams afterwards. And also doing the whole thing on flying robots, and just because we can, 2 flying robots, because why not? Now, so now I've kind of shown you some of the elements we have to put together into systems. Now I'm going to show you a system which is kind of like an abstraction of the Princess Leia R2-D2 problem. And here we have, this is the PhD work of Shokafir Pomer, who's at the back there. So this robot, its purpose in life is to take softballs from people and give them to somebody else. That's what it lives to do. And the interface to this robot, you don't really have to teach people. So in order to get the robot to take the softball from you, you offer it the softball. Right? And you don't have to tell people to do that. If the robot comes up to you and says, woo, and you offer the softball and it will come and take it from you. So now the robot has now seen Zhao's legs, now it sees Zhao's body, now it sees Zhao's skeleton, now it tells Zhao it's interested. Zhao is ignoring the robot. The robot tells Zhao, you have my attention, you just lost my attention. You know what the robot's thinking, right? I didn't have to explain that to you, I think. Shock effect's going to give the robot a clue. Whoop means I attended to you and I understand what you meant. Okay, now it sees the legs, sees the torso, sees the long bones of the skeleton, sees the reaching gesture. This guy wants a softball. Woo. All right. So we had teams of multiple people and a single robot. Now we have a team of 2 robots. How does she choose which robot gets the softball? She just offers it to the right one. And this robot will make the saddest sound possible. All right. So I said the robot sees legs, and then it sees a torso, and then it sees a skeleton, and then it sees the gesture. So underneath this super simple interface that we don't really have to teach people is actually pretty sophisticated software stack at this point. And the reason we have that is because the whole point of this research is to make the robot super robust so it always works. Or, for certain values always, nearly always works. That's very different from a lot of research robots which kind of work once or twice and then catch fire, but it doesn't matter because you got the video, so you publish the paper. Our robots are not like that. If they catch fire, which they have done, we build them again. So under the hood, we have a robust stack of sensing modalities, and we switch between them robustly and seamlessly. You don't feel any of that stuff. The robot just works, but under the hood, we do some fairly serious engineering, and that gets more and more true as we go on. Now, up to now, all the videos you've seen have been from our lab. Now, our lab is a special place, not just because of the tears and joy that go on in there, but because the lighting is very constant in our lab. So computer vision systems, some of you may have done some computer vision. The hardest part about computer vision is that when the lighting changes, everything changes. So if you're outdoors, the sun goes behind a cloud, the world looks like a completely different place to a computer system. Now, that may not be obvious to you because your brain is incredibly good at ignoring those differences. But imagine when the sun comes out, suddenly there are these strong, dark shadows everywhere. There are all these long, very prominent lines. Like the environment is dominated by these black light lines. You just don't see them, right? Your brain just ignores them because they're shadows. So that's the kind of problem we have to deal with outside. So the goal of the next period of our work was to try and scale this stuff out, get out of the lab so that the robots really work outdoors and try and do things over a large scale. So if you want to give R2-D2 the secret plans, but this is what R2-D2 looks like to you right now, you've got to get R2-D2 to come to you and then switch into here's the softball secret plans mode. Right? So it turned out no one had done this before. We looked for literature on this and we couldn't find any. So we have to figure out how do you make the robot come to you. Again, we're looking for interfaces which don't need any explaining to people, preferably. So we'd like to know, what do people do when you ask them, make the robot come to you? So we did an experiment where the instruction to the participant was stand there, make the robot come to you. That's it. That's all we say to them. And this is what people do. So the robot starts out 8 meters away. Everyone else apart from the waving woman is grad students in the lab being distracting. And this is what people do. So let me show you. We tried it with a bunch of people.
Robot, come. Robot, come here. Come to the robot. Come. Good job. Come. Stop.
Nobody's more Canadian than the freshly arrived Iranian grad student. So that's what people do. And we analyzed a lot of these things, and these are the dominant things that they do. So they make noises, right? We use that to get things attention. This wave, people do a lot. And this is kind of what you might do if you were trying to get someone's attention from the other side of a football stadium or something, right? You just can't ignore this. They also do this. Now, we like this because this means big changes on the computer vision system, right? You do a big signal and it's periodic. This is really, really hard to see. So we don't like that one at all. Turns out, well, people do that, but I think they would only do it over, I don't think you would do this across a football stadium, right? You would do this, but you wouldn't do that. But so the distance we have, we got both. And this lady did interesting. She was kind of steering the robot like this. There was only one person did that. The gentleman on the right, I'm not quite sure what his plan was, but he did nothing at all. He did it reliably. His strategy was to do nothing at all. Okay, so we decided that this was going to be a good one, right? This is the biggest of the signals, apart from the sound. We did some other stuff on sound. I don't have time to tell you about that today. So where our student Chris is in this scene somewhere, he wants the robot. Can you see where Chris is? You'll see Chris as soon as I start the video. You'll see Chris because he's doing this. So the motion is key to getting your attention. So Chris is tiny. He's about 11 pixels high at this point. And you see him now? He's kind of hiding in the trees there. The robot sees a patch of image which is changing with a fundamental frequency of about 2 Hertz. So it turns out that everybody, whether they're big or small, does this about 2 times a second. Okay. So we can pick out Chris. So this is not set up. These are just people coming and going from the bus loop. The robot ignores them. Now, ignoring them is actually kind of a challenge. So if you do this at 2 Hertz, unfortunately, you do this. Unfortunately, this is also 2 Hertz. So this is bad news. We've got 2 things going on. There's this, and there's the legs. So we have to work to ignore the legs. So the way we do this is, the nice thing about walking is you're moving with respect to the frame of reference of the world, right? You're moving with respect to the world. So we just ignore 2 Hertz signals unless they're stationary with respect to the world. That makes sense? So that's why the robot has to stop and look for the waving, right? I'll rewind that for a second. So see the robot stationary, finds Chris, ping, there he is, and then it kind of remembers where he was. And it stops and looks again, sees him again. Now, this is bad, right? So this works really well, and this actually has the record for the robot that can approach the person from the furthest away. It's the world record for that. But this is bad because we want to do our things on flying robots too. And as I told you before, when a robot's flying, his camera is moving all the time. So we can't do the be still trick. You just can't do it. If you try and hover stationarily, you can't. The robot's always making small adjustments, and the camera's moving a lot. So for this one, we had to build quite a complex processing pipeline. And right now, in order to cancel out the motion of the world, we have to actually understand the 3D structure of the world and then localize the robot with respect to the 3D structure to understand what's the world frame, the world coordinate frame. That make sense? So if you're moving relative to the trees and the ground, we ignore you. Now this is kind of state-of-the-art 3D, it's literally 3D reconstruction in real time. All we're doing is trying to ignore people who are moving. So in this case, we're trying to ignore Jens, who is running, and pay attention to Jake, who is waving. Now on this run, on the first run, we ignore everybody, just so you can see what the world looks like. When we come back, we'll turn things on, and we want to see Jake. Oh, here we go. So the robot waggles. You saw when the camera view changed a lot, the robot was waggling its rotors to indicate that it sees Jake. For a pilot, this is the signal for I see you, for someone on the ground, right? You seen that? If you're lost in the wilderness and a pilot comes by and waggles his wings at you, or her wings, that means they see you. Right. So this is the first time that we've been able to capture the attention of a UAV, a drone, in flight. My favorite thing about this is that all the computation is done on board the vehicle. When we did this, this was kind of just about on the edge of doable. That drone is, it desperately wants to fall out of the sky. It's carrying much too big a computer. It's much easier nowadays. Okay, so now we can get the drone's attention from far away. Under reasonable conditions in the lab, we can manipulate a drone's attention from a short distance. So let's put these things together. Let's build the first system that can get the attention of a UAV in flight, have it come, hover in front of your face. Now we're in the R2-D2 condition, and then we'll give it a command, a face-to-face command. So this is the PhD work of Mani Manajami from 2016. Again, we have people in the scene who are just random bystanders. We have a person detector that's really not terribly good, but it ignores everybody who is moving. It ignores everyone who isn't standing still and whose appearance changes with 2 Hertz. So now SEPA has been locked on, and the robot does this servo behavior that I'm really proud of. So the appearance of SEPA changed from tiny little SEPA to great big SEPA. Now it sees his face. This is the selfie command. Here's the selfie. And then this is the bye-bye command. I'm done. So that's the first example of being able to call a robot from far away, get it to come to you, give it another command. And the thing I'm really proud of on this, and Manny did fantastic work, is the scale change here. You start out very small, and that's how the robot perceives you in the end. And Manny won he was a runner-up in the best PhD thesis in computer vision in Canada in that year for this, and he won another prize as well. Now, just a word about this waving business. So I've shown you there's a lot of this waving going on, right? So why are we using this all the time? Well, we were using this because this was just at the very edge of what we could do with our computer vision systems. So we're pretty good at seeing faces. We can just about see hands okay, but we can see motion really well. So what we tried many things to get this working, and these motion gestures were robust and doable at the time, back 5 years ago. So this pink patch here is it's a spot of high motion if you take out the global motion from the rest of the scene. So we look in this box to the left of Manny's face and recognize the left-hand gesture, the right-hand gesture. This is very limiting and artificial, so this was always a placeholder until we could do this better. And then something happened in the last handful of years, is that the deep convolutional neural networks, that you've probably heard these words on TV or in college, if you're in college. Deep convolutional neural networks turn out to be a very powerful tool for recognizing objects under a wide variety of lighting conditions and size changes and all kinds of stuff in the real world. So this is a wonderful new tool that it's just perfect for our application. So before we just about saw faces okay, and then we would see motion, but now look what we can do. So it's genuinely new technology that just showed up. Now it looks like we're tracking these hands and faces, but we're not. We're actually detecting them independently in every frame. But it's so reliable that it looks like we're tracking. In fact, it looks better than any tracker. We used to have a tracker, we threw it away because we don't need it anymore. And apparently it makes everyone really happy. So this is the work of SEPA here on the front row. He modified a system which detected generic objects and tuned it so it detects only hands and faces, but it does it really well. So it's about as good as the best face detector in the world, and it is the best hand detector in the world, and does them both at the same time, 60 times a second. So now we'll put these things together, we can do some new things. So now the robot is autonomous all the time. Pratik is going to give the robot the takeoff command. The robot takes off and goes into the sky. Now it's looking for someone to interact with. Apparently it sees somebody in the bush there. If you stare into a bush long enough, you'll see just about anything. But no, the person in the bush is not waving their arms at 2 Hertz. So it picks SEPA. We put a bright light on the front of the robot so that SEPA knows he doesn't have to wave anymore. And then now instead of detecting simply the face and then motion, we're going to track SEPA's hands and face in detail. Now we can do a new thing. So SEPA can now grab control of the robot by doing this, and now he can fly the robot with his hand like a joystick. Because we use this as a safety measure. I'll only pay attention when he goes his hand up. Selfie gesture is this now. So now the robot will go down, up. Now there's a little delay on this. It's not super snappy because the data does a round trip over the wireless network to a laptop where we have a good GPU back to the robot again. It's a substantial amount of engineering goes into coping with that delay. So that's the absolute state of the art right now in gesture-based interaction with UAVs. And we have many of the firsts in this area. from getting the attention of the UAV in the first place, to calling the UAV down from the sky for the first time, to the state-of-the-art hand and face trap detector, to the using that in the loop. Now, right now, you can go buy a drone online that understands gestures. It will follow you around, understands the selfie gesture, and a couple of other gestures. So this one's made by DJI, who's an incredibly successful, well-funded Chinese company from Shenzhen. They have 500 or so really, really first-class engineers. And they are now 18 months behind my group. So we're done. There's just no point in doing this similar work anymore, right? So we've got a bunch of these first now. This whole industry has raced up behind us with this terrific stuff. It works great. If you want it, you can go buy it. They can't do everything they're not selling everything we can do yet, but they're really close. So it's time for my team to move on to the next thing and see what else we can stimulate a new industry with. A couple of things I'm going to tell you about really quickly. Pointing is a common gesture, right? Everybody can do it. This barely trained human can do it very well. You understand what she means. We understand what it's scalable. Everyone in the stadium understands what Bowie means. Animals can understand pointing too. There's a lot in that gesture. Interestingly, animals can do it as well, which is pretty cool, right? So you can understand what this animal means. He's pointing that way. Animals have been trained for hundreds, if not thousands of years to point to, there's a hunting dog, to point to where the bird fell into the grass so you can't see anymore. The dog knows where it is. Beta here has recently done a really solid piece of work where we take the hand and face detector. Now if we stand in front of an RGBD camera, that's a camera that gives us color and depth as well. We know where the hands and faces are really well, so we can isolate them from the image. So we now know how far away those pixels are. So it's fairly straightforward to take the points of the face in 3D, the points of the hand in 3D, and we fit a vector through them to tell what you're pointing at. And we do a little bit of cleverness to figure out exactly some statistics you can do on these point clouds to come up with a really good a vector that it points where you intended to point. And this stuff works great. You can download this code from our website if you want. It works with a Kinect, for example. So if you want to do human-robot interaction experiments with pointing, which lots and lots of people do, you don't have to roll your own code anymore. You can use ours. It works great. You can even point behind you, which other people have not done before, because the depth camera allows you to do that. Look how robustly we see her face. It just blows my mind that we can detect her face like that. Okay, one more thing. Following is really important. A lot of human-robot interaction work, a lot of authors have studied following. This was important enough that the magical brooms in 1940 Fantasia knew that following was important. So there's a big literature on following, has been for about 25 years. These days, they've got really, really good at it. So this is Big Dog from Boston Dynamics from a few years ago. Big Dog uses a mixture of LiDAR and computer vision to follow a person under very difficult circumstances, outdoors. This was a project they did for the US Marine Corps. This thing worked great. It really follows. Our observation was that, so following's actually pretty easy. You just keep the person kind of in the middle of your field of view and follow. Our observation is that sometimes you want the robot to be close to you while you're going somewhere, but you want it to be in front of you, not behind you. Right? So here's an example where the dog is out in front for a really, really good reason. Right? And in the case of the Big Dog, the Marine Corps robot, wouldn't it be better if Big Dog got blown up rather than the Marine who was in front? It just seems so simple. All you do is swap positions and keep it working. But it turned out that almost no one had done any work on this. So, and here's another example of an intelligent system that goes ahead of you for important reasons. So this is Payam's MSc, which he's just about finished writing up as we speak. I got a fresh copy warm in my bag. So this robot follows Payam, but follows in front of him. So it guesses where he wants to go, and it makes a map of the environment, and it figures out how Payam will probably interact with the environment, and then guesses where he's going to go. So here it's going to make a mistake. So Payam's interface that says, no, come this way, it's just like, nah, and the robot will zip in front of you. So this is the first system of its kind, and I think that there's a really interesting avenues here. If you imagine the robot getting further and further away, maybe it's flying, maybe it's driving, maybe it's in the supermarket, maybe it's in the hospital, I think there's a lot we can do with this, and it's a completely unexplored area. It's really interesting. So I'm really pleased with this, and think we're going to go places with this. What I really like about this is I want to get to the point where you can go on a long walk with a robot out in the countryside and just forget about the robot, and it will understand what you want. Okay, so what I've been telling you about, I think, is the vision of what we're trying to do is human-robot interaction like you always knew it should be. We want to interact with robots like we interact with other intelligent systems like trained animals. So that's our goal. And there's examples from culture and from engineering and from working with animals to go into this. And I think our group has found a special niche. There's no one else does work quite like this, and I'm really, really pleased with how the results have gone. So that's that. Now, who cares? Right. So what? We told you about all this stuff. I think coming into this room today, you didn't have any robot problems. You weren't distressed by your inability to interact with robots. It's just not a problem you actually have. If you have a robot, you probably have a Roomba which has a big button on that says clean. And you press that button and it just works. Or it'll fold your rugs up, usually. That's what it does with my rugs anyway. But you probably don't have a human-robot interaction problem. So why do we care about any of this stuff, apart from for niche applications? And I think we're going to care really soon. In fact, kind of now-ish, very, very soon. Cars are going to become autonomous robots right now. So I currently live in Silicon Valley, and if you drive through Mountain View in the middle of the daytime, I think last week I saw 5 autonomous Waymo cars at the same time. Right? I could see 5 from where I was parked, where I was at the traffic lights. These cars are real and they're around us. So consider this interaction, right? Let's say there's no driver in this car. This guy wants to be really confident that he's not going to get killed by this car. He's got to step out in front of it. What's the interaction mechanism here? So right now you make eye contact with the driver of the car, right? There's another move you can do, which is that you don't make eye contact, but you kind of ostentatiously don't make eye contact. And that means something completely different to the driver, right? So I dare you to kill me. It's a worrying one, right? But there's a lot, and this stuff is all well studied, right? Because it's really, really important. So these are kind of ideal conditions. This is in a light-controlled lab in Germany with a well-behaved driver in the middle of the crosswalk. They're also very well-behaved this is the most famous crosswalk in England, and everyone's behaving very regularly. If only it were like this in real life, but it's not like this in real life. So this is the second most famous crosswalk in the world after Abbey Road. This is Shinjuku Station in Tokyo, and it looks like this pretty much every night. Imagine now that half of these cars are robots, and there's nobody in them, or if there is, they're not driving. This is actually a pretty good situation because the cars and the people are well separated. There's kind of good discipline going on here. So maybe this is not too bad. This is India. And now imagine that half of these vehicles are robots. And they've got to get across there somehow. If they can't, they're no use at all. No one's going to buy them if they can't get across a standard crosswalk in the middle of the day. These people also have a right to expect not to be dead crossing the road. So the people have got to make progress. Everyone's got to be safe. We want to get some value out of these vehicles. We have to solve these problems. There's complex interactions going on between the drivers of all of these vehicles and all of these people all the time. And this is in every major city all over the world. Just in case you're thinking that, oh, of course, India is a special thing. This is Boston. This is also pretty wacky. It's kind of zoomed in view. People are everywhere, right? If that car in the middle is a robot, how are the people and the car going to interact? We can't have a system where the people are given a vocabulary of gestures and they give commands to the robot. That's not going to work. We have to use the gaze and attention of the person, maybe other aspects of the body language, maybe the way their body is facing, all these subtle things we can use. And the work I've done is kind of, I hope can offer some clues about how we can move forward with this. So why do we care about human-robot interaction? Well, you're going to be surrounded by expensive, deadly robots any day now. If you live in some parts of North America, you already are. And why do I care about that? Well, the reason that it's urgent that we work on that problem, on the cars, is because in North America alone, every year, 37,000 people are killed in car accidents. 37,000 people every year. And these robots will have the promise to drastically reduce that number right now. So it could be that in 5 years' time, that number is spectacularly lower. So that's 37,000 people killed in North America, 1.3 million people in the world. That's people killed, many more people are injured, but maybe permanently injured. So this is maybe the most urgent problem. There's nothing else I can do that's going to impact the lives of 1.3 million people, I think, with the technology that I know some things about and the trainees that I've worked with. So I think this is something urgent that we can do, and so therefore we should. So you should care about autonomous robots and interacting with them. This could be a wonderful thing that we do in our lifetimes, so that my children maybe have a greatly reduced chance of being among those groups. All right, to close then, Big Hero 6, you should go see it. There's tons of human-robot interaction in Big Hero 6, including mega swarms of tiny robots. It's a really cool movie. It has a very unusual thing. It's not technical, but it actually documents the experience of the life of being a robot grad student, like no other media I've ever seen. So this is what a robot grad student looks like from the point of view of the robot. It's highly accurate, I think. It's the middle of the night, the lab's a mess. This is trial number 33, he's very unhappy. Except until this happens. This is when it works the first time. And if you're wondering whether this is realistic, it's super realistic. They got it just right. So with that, I'll thank you very much for your attention. I'm happy to take questions that you have.
Well, thank you, Richard. What a fascinating talk. I can't help but think there's a bit of a metaphor, the fact we're moving from humans being followed by robots to humans now following robots, and where that's taking us. But I'm sure people have questions or comments they'd like you to respond to, so we have some time for a few, and then I understand we may even have time for a demonstration after that. So who wants to go first in terms of putting a question? Right here.
Yes.
Oh, wait a second. We gotta get a microphone to you so that the people watching on video can hear you. There we go. There we go.
Hi. So I'm an undergrad student in SFU MSc, and I might not have very knowledge about what I'm asking, but as I see outside in society, we use gyroscopes and a stabilizer for camera to stay steady, right? Why can't we use that in our drone to look down steadily?
Yeah, it's a good question. So you can, it does help, but there's always a certain amount of movement of the vehicle that is too much for the gimbal mechanism to deal with. So it's you're right that there are things that make it so your camera doesn't have to swing the same as the vehicle, but it always swings a little bit. But you're quite right.
Anyone else have a question? Right, just down the row here.
Yeah, thank you for a great presentation. You mentioned culture several times. It looked like it's very natural for you to collaborate with anthropologists. And actually, I think it can be beneficial both ways. Have you ever thought about this?
I've never collaborated with an anthropologist. I have collaborated with a bunch of cognitive scientists and psychologists and behavioral ecologists, and very, very fruitfully. So I have a at least I used to have a visiting position in the behavioral ecology group at SFU, for example, took that stuff seriously. So a long time ago, I made the first robot that controls the behavior of an animal with my sheepdog, as President Petter mentioned. And so I've taken the animal behavior very seriously since I was a teenager. That's actually why I got into the artificial intelligence business, is because I wanted to understand how animals worked. That was what interested 17-year-old me, and still does. So a friend of mine in England described robotics as a theory of mind with a screwdriver. And so that's my enterprise, theory of mind with a screwdriver.
Okay, a couple of great questions. I'm sure others have thoughts. Oh, right over here. So Heather, if you want to come over here or we've got a microphone here, great.
You mentioned about how the neural networks changed the game from tracking to detection. Could you expand more on that?
Richard, maybe you can repeat the question
sure.
so
The
people in
question
the
was,
back can hear.
I mentioned how neural networks changed the game from tracking to detection. I wouldn't say that they didn't change the game. They changed where the trade-offs lie. So it's not completely different. So before we would use detectors, and then the detectors weren't very good. We would use very, very good, time working on very clever trackers. You would occasionally see something in roughly the right position. So you'd put a huge amount of work making models of how things move so that you could kind of glue these clues together to get a good estimate for where things are. And now we can get great detections, as you saw. There was no tracker in there. So we can put way less resources into tracking. We can use very simple trackers, or in some cases just omit the tracker. But now we're flying a several $100 GPU to do the computation for the detector, which is new. So we traded resources for the technology that works best. So they moved the kind of the trade-off landscape.
Anyone else? Back over here. Heather will come up on this side and hand you a microphone.
Hi, I'm a PhD student here at MSc. I wanted to know, like, what is the time constant of the loop when you include vision-based cameras for the control of the drones or robots? What is the maximum time constant you got?
If I understand the question correctly, so I think we're updating about 25 hertz, 30 hertz, and that stuff. Yeah, it's about 30 hertz. Is that what you mean? So with the frame rate is 30 hertz, and unfortunately we have a very long delay because of the image compression and the Wi-Fi round trip is bad. So the delay is what, 300 milliseconds? Yeah, which is for a control system that's forever. So Manny wrote a very, very good model-based controller which can compensate for this very, very long delay and have the vehicle fly reasonably well. So this long servo thing, it looks like nothing, right? The vehicle just flies in a straight line from over there to your face. It's one of the pieces I'm most proud of because it's very, very difficult to do with a third of a second delay. But it works great.
Okay, one more question. Okay, what was the controller or control systems you used for this drones especially?
The control system? There were many of them. There's a very layered model predictive control system with all kinds of stuff in it. You come and see me afterwards, I'll tell you everything I can remember.
Okay, sure, thanks.
And
Here's an offer.
all the papers are all on my lab website. You can read it at your leisure.
Anyone else? Yeah, down here. And then we'll take a couple more, and then can we do a demonstration? Are we able to do it?
Yeah.
Looks like we will.
Do it.
Okay, right.
Yeah.
Hi there. First, I wanted to say I was thoroughly impressed and really excited by the presentation.
Thank you.
So you demonstrated that with the one that could deliver the softballs, that it's able to understand the same direction and instructions from different people. And I'm just curious as to what your thoughts are and your goals towards actual facial recognition and being able to interpret instructions from multiple people and being able to prioritize instructions based on a familiar face.
Yeah, so that's a great question. And I have a paper that addresses exactly that, where we could identify people. I didn't have time to include that one, but we have a system where you have N robots and N people, and everyone looks at the robot they want, and they sort themselves out optimally, for example. So you can look that up on the website if you want to, but it's a good question. So in terms of a little anecdote for doing things, treating people individually, so the trick for when we have the robot fly from far away and kind of park itself 2 meters in front of my face, we can't actually measure this distance, right? We don't have a sensor that can measure how far away the person is. So instead, we have a prior that says people are about this tall, right? So I'll get it so the person looks about this big. But this has the cool side effect that for me, the robot is quite a long way away. For children, the robot's really close to their face. So we didn't try it on anybody who was less than 1.5 meters tall for safety reasons.
Oh.
Maybe I shouldn't tell that story.
Chance for one last question. There's one way over here in the back. Let's give this gentleman a chance, and then we'll see if we can get the demonstration going.
Hi, I'm Mohammed from MSc, graduate student. So my question regarding is like the...
Just hold it closer to
It's
your face.
working. You just have to speak up a little.
Okay. It's like my question regarding the kind of communication that you do for human-robot interaction. It's like a human uses like multimodal. I agree with you when you do it, for example, in long distance and with a drone. Yes, there is no way, for example, to use the voice. But when the robot is very close to us, why it's like you insist it's like using one way is like the vision system. Maybe it's like the voice. In this case, it's like bring a lot of information, especially with natural language understanding now.
Yep.
So my question is like, what do you see about using the multimodal is like with this human-robot interaction?
Yeah, your observation is quite correct. So voice is a very common way that people do in HRI. There's tons of work on that, lots and lots of people doing it. I want to do something a little bit different. That's all. I don't think it's bad. I just want to do something else. Try and do the other 5% that other people don't do. Yeah. In fact, we did. You know, when she said you too, not you. So there's an example where we used it.
All right, so can we do the
Yeah,
demonstration?
it's kind of running right now. Let me get, if I get in front of the spots. So I wanted to make sure that the robot could feel your presence. So give it a wave. See? So your hands and faces. So it's a little bit nasty. There you go. So you've now, so we decided not to fly the robot in here for obvious reasons, but the robot can feel your presence there. Maybe the back here a little bit too small for it. It's a little dark in here, but there you go. So you've, the robot can smell you. All right. So thanks very much for your attention, guys. I enjoyed it.
So we all became a collective demonstration of human-robot interaction, as was appropriate given the topic. And I look forward to the next lecture being delivered by a robot, but that won't be happening anytime soon. Well, you've already thanked Richard quite appropriately for just a fascinating lecture about an area which, even if we didn't come in here thinking it was important, I don't think any of us can leave not understanding that this is going to be a real important part of our lives going forward. And the way in which we and robots interact is obviously going to be important as well as we watch that unfold. So thank you so very much. And Richard, I think, kindly has agreed to stay back for a reception afterwards so you can ask some further questions. I also want to thank our wonderful volunteers, Kevin and Louie, and Heather Sanders from my office, who helps to set up these lectures right back here. So thank you for helping out. And let me just tell you about two other lectures that are coming up